All right, good morning everybody. Let's get started. Here is what we are going to do today. Just as last time, I will have a short ride through basic terms and concepts of probability theory. To a certain extent, I will repeat a couple of the things we discussed last time, and I will get back to a question that has been raised and try to answer that question. And then we will briefly look into what we did last time when we talked about intensity normalization and histogram equalization. And I call it recap, but there's actually going to be some additional new material today which we can look into because we will do something here. And in the second half of our lecture today, we will begin studying a problem, namely the problem like what to do with images that show scenes where the illumination is inhomogeneous to a certain extent, and can we somehow normalize inhomogeneous illumination conditions. So that is our menu for today, and without further ado, let's get started. Last time we already looked into the notion of the expectation of a function of a random variable, and let's say for the sake of the argument and sake of simplicity, the random variable we are considering is called capital X, and it assumes values in the real numbers. And let's also assume that that random variable was distributed according to a probability density function P of X. And if we then consider a function f that takes values in the reals and produces values in the reals, we might actually look at what happens sort of if we apply this function f to the random variable we are dealing with, and ask for the sort of, say, a most likely outcome of the application to that function. And last time, we already saw that this crazy construct here, this funny letter E of a function f of x, is defined as the integral f of x times p of x dx. In contrast to what we looked at last time, where's the difference to what we did last time? There is a tiny but probably crucial difference here. So in contrast to what we did last time, I'm actually indicating the domain over which we integrate. Right? And I don't have something up here. This is basically to say we are integrating over all the real numbers. One of the special cases we can look into or look at if we consider this concept of expectation is the expectation of the random variable itself, which is to say if the function f we considered in this definition here is the identity function. But then instead of f of x, we just plug in x here and have that the expectation of x is the integral over, in our case, all the real numbers, x times p of x dx. And last time, we called the result of this integral, we called it mu. Greek letter mu here. And so let's ever so briefly think about what that means. So we have an integral, and it's not indefinite. There is actually we integrate over something. What is the result of such an integration? It is a number. All right, a number. What would be the result of an integration like that? A number. All right? This does not produce a function, so this operation here does not produce a function, but it produces a number if we are given this function f of x. And I said, I didn't make it explicit, but I'll do it now, that this operator here is a linear operator. And this is because, first of all, we may look at the expectation of a constant times a function. And we plug this into our definition of what it means to compute the expectation. And we find it's the integral over all real numbers, c times f of x times p of x dx. And of course, we can pull out the c out of the integration because it's a constant, it does not depend on x. If we do this, there we go, I pull it out. But then that is c times the expectation of x. So that is first thing we note. And the second thing is that if we look at the expectation of the sum of two functions, say f of x and g of x, and we add them together, and we plug this expression into our definition of what it means to compute the expectation, we find that this is given by integral over all the real numbers f of x plus g of x in parentheses times p of x dx. Now, of course, we can expand this integral by just multiplying the p of x dx into this sum here, and we end up with two integrals. First one is over all the real numbers f of x, blah blah. Second one is over all the real numbers g of x times p of x dx. But this is the expectation of f of x, and this is the expectation of g of x. And there you have it. This is what we need to be sure that this indeed is a linear operation. If we consider the expectation of the constant times this, it is the constant times the expectation. And if we consider the expectation of a sum of things, then it's the sum of expectations. And we now made that precise. And here is the answer, getting back to a question that was raised last time. This operation is also idempotent, as we say. And that is to say, if we are given the expectation of a function f of x, we just again plug in the definition of what it means to compute that. And we already agreed that this operation here produces a number. And now I'm calling this number eta, and this is the Greek letter eta. We can then ask for the expectation of the expectation of f of x. But given what we just computed, this is the expectation of eta. We can agree on that, right? Good. Then let's plug in this value into our definition of what it means to compute the expectation. So we have, in our case, still the integral over all the real numbers, eta times p of x dx. Now we can again pull out the eta out of the integration because it is a constant that does not depend on the variable of integration. Here we go. It's eta times the integral p of x dx. What is this? 1. Right? And that is to say that the expectation of f of x is eta, which is another way for us to denote this. So there you have it. This is indeed, if we compute expectation of an expected value, we get the expected value back. And because of that, we can then, if we look into the definition of the variance, which we did last time, which, is just to say that, again, we are considering a random variable, let's call it capital X, and again, let's assume that this is a variable that assumes values in the real numbers, and that its values are distributed according to density P of X. And again, we have a function that takes real numbers and produces real numbers. We can then define the notion of the variance of f of x as the expectation of the squared difference of f of x minus the expectation of f of x. And again, an important special case is where we consider this function f of x to be the identity function. In that case, we, instead of writing f of x, we plug in x's here. And we find, well, if we call the expectation of x, if we call it mu, then this becomes the expectation of x minus mu squared. And this thing was called sigma squared last time. Lots of Greek letters here. I'm using those Greek letters because everybody does. This is the Greek letter mu, sort of the Greek equivalence to the Latin letter M. And this is the Greek letter sigma, sort of the Greek equivalent to S. And the question was raised in this context. I said that we can understand this notion of the variance of the function f of x, and again note that I am dropping the of x's here just for notational, to remove notational clutter. If we go back here, you know, first expand the square, then we have f squared minus 2 f e of f plus e of f squared. So this is basically what we have here, and we just convinced ourselves that this is indeed a linear operation, so we can write it like that. And last time there was the question, well, what happens if we apply this e to this thing here? And we just saw nothing. That is what we went through when I said it's idempotent. And so therefore we can indeed write the variance of a function f of a random variable as the expectation of the function squared minus the square of the expectation. We also already looked into the notion of covariance that addresses the case of having to deal with two random variables. Let's call the values of these random variables x and y. Then we might ask, so what happens if, say, I don't know, x becomes large? Does y also become large, or does y shrink? Do they vary together, or are they anti-correlated, or are they totally uncorrelated? These questions can be answered by looking into the covariance of these two variables, which is defined like that. And again, if we expand this product here, we can also write it like this. And covariance will be actually an important concept for us throughout this semester. I will begin seeing that today. If the random variable we are dealing with was a vector or a vector valued variable, we could call the possible values of this random variable capital X, we could call them vector X, and we would assume that they were distributed according to some density P of X, which is now a higher dimensional density, so it's not just, density over a line of numbers, but say some space, or some function defined over some space. But again, we will call the expectation of x, just call it mu, vector mu in this case. For random vectors, we would have that this notion of covariance becomes a matrix. Right? This is expressed by the fact that we consider an outer product here. Outer product between two vectors gives us a matrix. And we have to evaluate this outer product with respect to the whole space over which this is defined. And I just realized that, again, I have dropped the sort of boundaries of integration, which is an accident here. Actually, for today, I wanted to have them in all the integrals and all. But, you have to learn to adapt to context. So that is to say, in particular, when it comes to probability theory, notation really is a mess. It is like that. And I remember that being a student, I was suffering from that. It was hard for me to, like, why is that? What? Why is it like this? And because, people write this P regardless of whether it's a probability density or probability mass function. Those two things mean something different, but they are written using the same symbols. And sometimes people write these indefinite integrals, but they actually should be definite integrals. So yeah, I'm sorry about this. I'm basically repeating the stuff that drove me mad as a student. But the fact that I'm doing that actually shows that with time, you know, you adjust to that. And eventually you can live with this sort of notational ambiguities here. And if we look at the definition of what it means to compute a covariance matrix, we again recognize it as an expectation. So this is just a generalization of what we called the variance for the case of one-dimensional variables. And again, we might multiply out this product here and see, if we were to do it, that this could actually be indeed again expressed as the expectation of the outer product of all the x vectors we are dealing with minus the outer product of their mean vectors mu. And last time we also looked into this important example, an example where we are dealing with a finite set of vectors, and the number of vectors does not really matter to me, and if the number does not matter, I usually refer to it as lowercase n. So we are given n vectors, and each of these vectors is a real valued vectors in m dimensions. So if from now on I may either drop the n or the r here, so typically we are dealing with real valued vectors, and the dimension does not really matter to me, so I'll refer to it as m. If I, for some reason, forget these kind of important details, then a fallback for you is always to assume, okay, there are n vectors, and there are real valued vectors, and they are n-dimensional. Should we be dealing with complex valued vectors, I will point that out explicitly, all right? Now, if we're given n such m-dimensional vectors, then of course their expectation is an m-dimensional vector as well. I'll call it mu. And we shall also assume, for the sake of simplicity, this is what we often do in practice, that these n vectors here are identically distributed, that is, it is equally likely to observe any of those. Mathematically, we would say that the probability of observing one of these vectors, xi, out of these n vectors is 1 over n. Right? But then we can plug all this information into our definition of what it means to compute a covariance matrix. In contrast to the previous slide where we had the integral, because we were talking basically about a continued number or a continuum of vectors, now we are just dealing with a discrete set. So integration becomes summation. The p of x, which was here, let's go back to this thing, p of x, dx goes away because we're talking about sums here, but the p of x, this thing here is the same for every term in this sum, so we can pull it out. That's what I did here. We can happily compute all of this. We already did this last time. But what I forgot, and this is why I'm repeating it here, is that the covariance matrix that results from these computations is actually a square matrix of dimensions m by n, where m is the dimension of the vectors we are talking about. And here is something we did not already talk about last time. Let me just define a matrix M, and let me define it as 1 over n, n being the number of vectors we are given, times the sum over all the vectors we are given, and the terms within the sum are the outer products of the vectors we are given. So I define a matrix M as 1 over n, sum over all the I, vector xi times vector xi transpose, which is my way of indicating the outer product here. And if we expand this sum, we have 1 over m x1, x1 transpose, plus x2, x2 transpose, and so on, up until xn, xn transpose. And yeah, we also note that if we were to expand these vectors in terms of their elements, we could write the KL entry of this matrix as 1 over m sum over only I xik times xil, where the I in this case still counts like the vectors we are considering, and k is the kth entry of vector I, xi, and L is the lth entry of vector xi. This is the notation I'm using here, and I consider this so elementary that I will not, make it explicit, but would encourage you to verify this at home. And if we now define a matrix like this, I call it capital X, such that this matrix consists, row-wise, consists of the vectors we are given, x1, x2, all the way up to xn. These vectors, these n vectors, form the rows of this matrix X, which is to say that we are talking about a matrix with n rows and m columns. And if we look at the transpose of this matrix, then this is of course a matrix with m rows and n columns. I just transposed this one. Then, however, the product x transpose times x is an m by n matrix. All right? Because if we have an m by n matrix times an n by m matrix, that gives us an m by m matrix. All right? So this actually, maybe I should have shown it in red. It's very crucial if we're talking about m-dimensional vectors and collect them in matrices like that, then the product x transpose times x gives us an m by m matrix, a square matrix. We can then ask for the KL entry of that matrix, and here we are dealing with the product of two matrices, and well, this is how the KL entry of this product is defined mathematically, product of two matrices. Here we have x transposed ki, which is basically to say this is xi k if we sort of untranspose it. But this is what we just considered. Where was it? Where was it? Here, there. Right? So this thing is the same as that. And that is to say that this matrix M we defined, can be written as the product of x transpose times x normalized by some factor 1 over n. But what is that? It's the covariance matrix. So in that sense, from now on, whenever this thing here appears, and it will appear a lot, you can understand it as a covariance matrix. Quite often I might be missing this 1 over n thing here. This is not really important to me because it is just a factor. But from now on, if you see this and it appears sort of, funny to you, what does that mean? Think covariance matrix. All right. But now we have to look into something else, something we did not really look into last times. Namely the idea of the change of continuous random variables. And what I mean by that is, if we consider a random variable, and again assume, for the sake of simplicity, it is enough for us in this course, that this random variable would assume values in the real numbers, and let us assume that they are distributed according to some probability density p, and I'm using the subscript x here to indicate that this is the distribution of this random variable. So they are distributed, I'm using this tilde thing there to indicate that, according to px of x. And then we also consider a random variable y, which also assumes values in the real numbers. And we assume that this y results from a transformation of x. And I sort of highlighted the important requirement that this transformation is monotonous. So either is something that grows or declines, but it does not grow and decline. Whatever. It's monotonous. Either grows or either declines. It has to be monotonous. Well, then we have a new random variable, and it will be, distributed according to another distribution. And therefore, I'm using the subscript capital Y here to indicate that this random variable is distributed according to some distribution which is different from that one. Right? And our question at this point is, if Y is produced from X like so, can we say something about Py? Can somebody already tell me something about this? I need an honest answer here, because, well, depending on your background, this may be, really elementary stuff, or stuff you have never heard of. If it is stuff you have never heard of, I encourage you to tell me so, because then I can adopt the remainder of our semester. Right? So you don't have to tell me right now, but maybe after the lecture, come see me and say, I have never seen this before. If you have not seen this before. Have you seen this before? That is the question. Is indeed, if we know the distribution of the random variable x, and we know the transformation t, then we know that the distribution of the random variable y can be expressed in terms of the distribution of the random variable x, where py of y is given by px of the inverse transform of t, like t inverse of y, times the norm of the derivative of the inverse of y with respect to y. So if that is new to you, then please tell me so later on, because I'll then have to adapt what we are doing in this lecture. Here is an example. What is this? What was the name of this distribution? Gaussian. It's the Gaussian, exactly. So apparently we are dealing with a random variable x that is distributed according to some Gaussian with a certain mean, mu, and a certain variance, sigma squared. I don't really care about the mean and the variance here. But let us assume that we produce a new variable y as a transformation of x, where we just say y is e raised to the power of x. This is some transformation mechanism. It's certainly monotonous, because the exponential function is definitely monotonous. So this is it meets the requirement I sneaked in onto this slide here. This is a monotonous transformation. Then we can look at the inverse transform. So basically, say we are given the y, what would be the value of x, which is of course, in our case, just the logarithm of y. Can ask for the derivative of the logarithm, which is just 1 over y. Right? And if we plug that in to the equation we saw 2 slides ago, we find that the distribution py of y is given as the distribution px of t inverse of y times the norm of dy t inverse of y, which is 1 over square root of 2 pi times sigma, and then there's 1 over y, which is this thing, which is this thing. Right? This 1 over y comes from here. And here we have e to the minus 1 over 2 ln y, which is basically this here. So instead of px of x, we have px of t inverse of y, which is ln y. The rest does not depend on x. So here you have it. We have e to the minus 1 over 2 ln y minus mu squared over sigma squared. What is the name of this distribution? Have you seen that before? No. It is called the log normal distribution. Here is the distribution we begin with. I don't know. Mu seems to be some 1.5, whatever. I have to look it up in the script I used to produce this picture here. This is the distribution we begin with, parameterized with a certain value for mu and a certain value for sigma square, which I really don't recall at this point. And then I have, drawn a couple of points from this distribution, 100 points, and as we would expect, a sort of cluster around the mean of this distribution. Nothing special here. And then, on the next slide, I have computed e to these values and plotted the resulting distribution, and it looks like this. Right. Note that if we compute e of something negative, it still leaves something positive. So all the dots move over here if we consider that transformation. And the density now is skewed. This is one picture of the so-called log normal distribution, whereas the normal or Gaussian distribution is symmetric, the log normal is definitely not. Right? Here we see an example of a transformation of continuous random variables. All right, and we will need that in a second, because last time we talked about histogram normalization and equalization, which, if you remember, was dealing with the problem of trying to improve, say, either overly dark or overly bright images, basically images of low contrast. Can we do something about them? Can we use sort of the mathematics we know about images? We know that image processing is just playing around with mathematics. Can we use that to enhance the contrast? And here we already see that we can do this. This is the normalized version of this image, and over there that is the equalized version of that image. Now, how did this work? Basic idea was once again, and note that I'm abstracting the notation. What I used last time reappears here, but it's slightly more abstract. The basic idea was, of course, sort of as always, to consider digital intensity images as partial functions, which is to say they are defined over discrete pixel coordinates. So they're defined over a plane, and we only look at sort of discrete coordinates, so we can understand it as a function from n square, n indicating the natural numbers, to a set C, which is an unfortunate name clash with the covariance matrix, but this has nothing to do with covariance matrix. This is sort of C is color here. But we are talking about intensity images, so the colors assume values between 0, 1, all the way up to L minus 1, where L typically is 256, intensity images here. And it is a partial function because in the real world, not every possible combination of two natural numbers actually occurs as the coordinate of a pixel. So I don't know if that was 52 billion, would be the one, and the other would be, I don't know, 80 trillion, and that would be a very, very large image. We typically don't deal with images of that size, so in that sense it's a partial function. It takes x and y coordinates, or I and j coordinates, however you like to call them, and some of them are actually being assigned an intensity value, but not all of them, so it's a partial function. And we looked into the idea of applying transformations to this set of intensity values. And, oh, look at this. This looks familiar now, right? We talked about this just a few seconds ago. Let's say that, the intensity value of a pixel is basically a random variable. And let's, I don't know, call the intensities in the given image, let's call the values x. And it's a random, like depends on what pixel we look at, might be a different intensity than for another pixel. So it's random in a certain sense. I shall call them x, and then we want to do something to the intensities. So it's basically we sort of consider a transformation between random variables, producing another one, which I call y, just as before. And for the intensity normalization, we looked at the idea of sort of stretching the given intensities in an image which range from x min to x max, stretch them such that they cover the whole range from 0 to L minus 1, typically from 0 to 255. Here is how that looked like. So here's the dark image, here's the normalized image, this is the histogram of the dark image. We see that somehow the intensity values seem to reside in this subinterval, say from 0 to something slightly larger than 128. And if we compute this normalization, then all of a sudden they range from 0 all the way to 255. Why or how does this work? Well, this is just an instance of this familiar mapping between two intervals. Here I do assume that we are given an interval ranging from x min to x max. Real valued numbers here, and we're given another interval ranging from y min to y max, and I require that x min really is less than x max and y min is really less than y max. I basically need it so that this does not become 0. But then we can understand the mapping of a number x in this interval to number y in this interval as sort of this simple scaling plus translation. And we discussed this in detail in the last semester, so we really do not have to look into this again at this point. The thing to note is that in the last semester we did it with respect to pixel coordinates, and now we do it with respect to pixel intensities. This is all boring. Way more interesting is the question of histogram equalization. So to recall it, we thought of it as trying to turn the histogram of the given image, overly dark or overly bright, into a more uniform histogram. And this is how we computed that. And again, the notation has become more abstract, because last time there were some quotients here. Right, it's gone now. The reason why that is gone is that I now assume the histogram of the image we are given, the overly dark or overly bright image, this histogram is normalized. That is to say that we divide every entry in each of the bins of this histogram by the total number of pixels in the image we are given. If it is normalized, then the cumulative histogram will assume a value of 1 if the largest bin corresponds to a value of L minus 1. Right? So this is the difference to what we discussed last time. Last time it was not normalized, but I had the normalization sort of contained in the equation. Now there is no normalization because I assume that happens in advance. So I assume the histogram to be normalized such that the cumulative histogram assumes a value of 1 for the last bin. Here is the effect of that. Once again, the overly dark image, its histogram, its cumulative histogram, then the equalized image. Histogram has changed, but the most important thing is that the cumulative histogram now looks very linear. That is what has happened here. Now, why or how does that work? This is something we could not answer last time because we had not yet looked into the idea or the mechanism of transforming random variables. Now we can understand this. Let's see. to sort of simplify our argument. Sometimes it's indeed easier to talk about something more difficult than about something simple to expose a general idea. And so instead of talking about histograms, I will now talk about, again, random variables, but I will not assume them to be discrete valued, assuming, say, values between 0 and 255, but assuming values in a continuum between, say, 0 and 255. So we're talking about real valued variables now, and both of them are supposed to assume values in this interval here, continuous. And well, we are given this image that is overly dark or overly bright, so we do know the distribution of the intensities in this image. We may not be able to express it in terms of a closed form solution, but we can, you know, compute it from what we are given. And we do want to transform the histogram, or the random value x that indicates the intensities in the image we are given, to obtain new intensities y. And well, we assume that this transformation maps the interval from 0 to L minus 1 to the interval from 0 to L minus 1. So it's like, you know, domain and range are the same because these are the intensities we are given, these are the intensities we want to produce. And it should not leave that domain. So domain and range are the same. And once again, a very important thing is we need this T to be monotonous in order for all of this to work mathematically, otherwise we would have a dire problem. And actually we constrain it such that an intensity of 0 will be mapped to an intensity of 0. Right, this is what we want. And an intensity of L minus 1, say 255, should remain at 255. Has to be, so we require that T to take the intensity interval, to map it to the intensity interval. We require it to be monotonous. We require it to be invariant at 0 and L minus 1. And our goal is to determine a transformation T such that if we look at the cumulative density function of this random variable y, it should look like, so if we evaluate this integral from 0 to y, py of z dz, note that I'm using the z here only because the y appears as a boundary of integration. If there was no y here but some number, I could use y's, but since the y, the random variable itself, occurs as a boundary of integration, I have to use something else here. This is just for notation, right? There's no deeper meaning. But we want this cumulative density to be of that form because this is linear in y. This is what we want to have. And it's supposed to be linear. It is linear in y. And if we evaluate this thing at 0, well then it is 0, which is sort of, when you go back here, what we wanted. And if we plug in L minus 1 here, then it goes to 1. And this is a good thing for us to require from a cumulative density function. So this is our goal. We want to determine a transformation T such that the resulting density, if we integrate it, has this form. And now consider this. So we look at the density Py of z dz. We integrate that from 0 to y. And given what we just discussed, right, we can write this expression as px t inverse of z times the norm d dz t inverse of z dz. This is what we did a couple of minutes ago. I have just substituted this by the corresponding expression in px. Now for the left-hand side, we already agreed that we want this to evaluate to that. Right, so I just repeat that here. Just to say, on the left-hand side, we have this, on the right-hand side, still that. And now, we can write this like so. Does anybody know what I did here? What have I used here? There is a theorem in calculus. Not quite. It's called the change of variable theorem, but it has to do with substitution. Right? So this is indeed a fact of calculus, that we can write this like so. This is actually the reason, well, now we're using it in the other direction, but this is in fact the reason why this density can be written like that. So this is the usual way of how you would apply this theorem from calculus. Now I applied it in the inverse direction. We are already given sort of this expression in T inverse. And instead of integrating from 0 to y over this density here, we may integrate from 0 to T inverse of y over this density. It's a fact from calculus. Okay. But T inverse of y is x. Right? So instead of T inverse of y, I can write x here. But y is T of x. Alright? Can do that. But this establishes that T of x is L minus 1 times this integral. Let's go back. If we multiply both sides by L minus 1, we are there. So for the continuous case, we have found the transformation we are after. We wanted to find a transformation of the random variable x, which indicates intensities in our case right now, such that the resulting random variable y has a linear continuous density function. And this is the result. Now this was done with respect to continuous variables, but in the discrete case, the case we are actually dealing with, we can think of these continuous densities as the normalized histograms, and we can think of these cumulative density functions as the corresponding cumulative histograms. And there you have it. This is why this idea of histogram equalization works. Okay, and now for something else. For the rest of this lecture, we'll now study the following problem. We want to cope with inhomogeneous illumination conditions. And this is to say, let me give an example. So here is the image of a cat. And it seems that when this picture was taken, there was a light source somewhere over here illuminating the face of the cat, because the face of the cat is brighter on the right-hand side than it is on the left-hand side. And our question is, can we do something to the image so that on average it is well, of equal average equal brightness on both sides? This is not really very convincing, I know that. Basically what has happened is that everything has become darker and the whiskers are still very bright, but that's an artifact of this image. You can probably look at another example. What I did can be done slightly better. So the problem we are after is sort of turning images like that into images like that, which are of more equal intensities across all the pixels. And the approach we are going to follow is that we will try to estimate an illumination function. And whenever I use the word estimate, we know that we are dealing with an optimization problem. And I told you that this semester is all about optimization. Once we have estimated that function, we may try to neutralize its effect. And let's see how that can be done. Okay, that is to say, our main topic for today is the problem of illumination compensation. And without further ado, we will have to start with certain assumptions. Because basically this is a very ill-posed problem. We know nothing about the situation under which an image was recorded. We're just given the image and we find that it is, say, somewhat brighter on the right-hand side than on the left-hand side, or in the upper half and the lower half. Like, I don't know, there's some inhomogeneous illumination going on, but we don't really know under which conditions the image has been recorded. If we had perfect knowledge as to the position of the camera, and the position of the light sources, and the intensity of the light, and we were given the resulting image, then we could use all this information to sort of, improve on the artifacts we want to get rid of. But if we're just given the image, we know nothing. And since we know nothing, we have to brutally assume something. We have to make certain assumptions. Or we have to posit a model. And our model is as follows. We assume the following general model, sort of image formation. The idea is to say that an image is the result of illumination. I just talked about this, illumination. And here's a new word, reflectance. And I'll talk about this in a minute. Reflectance of a recorded scene. Recorded scene. And I'm going to switch to pen. Illumination and reflectance, and red is just because it is more saturated. That is to say, we assume that the image is a function, and now something rather unhappy happens because I assume that this is a function over spatial coordinates x and y, and just a few minutes ago x and y were indicating intensities, but now they are not. Now this is sort of x and y as in a function defined over x and y. But now the x and y has nothing to do with intensities, it's basically spatial locations of pixels. So this is the image we are given, x and y, and we assume, this is our general model, it to be a product of an image I of x and y times an image R of x and y, where I is supposed to refer to illumination and R is supposed to refer to reflectance. Now what does that mean? Look at my shirt. It is white and blue striped and I don't know, squarey shirt. It is being illuminated by, I don't know, the light sources in this room and the light outside of this room. And together, a couple of lamps under the ceiling and all the sunlight incident to the windows illuminates my shirt. And this is rather homogeneous under the conditions we're talking about here. But what you see is not just due to the illumination of my shirt, but also due to what it reflects. And at parts where my shirt is white, it reflects more than at parts where it is blue. And then there are these buttons which reflect the incident light in a different manner than the rest of my shirt. And then there might be a different reflection where there are, you know, these creases in my shirt. But what you see about me and my shirt in particular is somehow a combination of the illumination and what is being reflected. Right? So that is to explain the notion of reflectance. And from what I just said, we can further specify our model, which so far states that what we record as an image is a combination of illumination and reflectance. And I already said, yeah, so the reflectance depends on the material properties of the shirt, which are different when it comes to buttons, and it depends on the creases of the shirt, so the physical properties of that shirt. And illumination basically depends on these lights on the ceiling and the light incident in the windows, which seems to vary, you know, more smoothly or less drastically than my shirt. So we can specify or further specify our model by saying that compared to the scene reflectance, the illumination is a slowly varying function. Is that true in general? Most certainly not. If there was a stroboscope here and I would be illuminated by a stroboscope, then that would not be true. But what can we do? We are dealing with an image of inhomogeneous intensity distributions. We have no clue as to how this image was recorded, so we have to require certain assumptions or make certain assumptions if we want to do mathematics, and this is what we assume, which certainly is not true in general, right? But what can we do? All of this is to say, once more, that reflectance depends on properties of the objects in the scene. I say scene objects, and different objects have different properties. So once again, we could think of the my shirt. The buttons are physically different objects than the shirt itself, and they have different reflectance properties. So reflectance varies more quickly or more drastically than scene illumination. Let me note that as well. So this is common sense about reflectance and illumination. Illumination generally depends only on a few light sources. So this is, you know, sort of common sense. There's not much more to explain these assumptions of ours. But of course, even though we can assume things like that does not really help us any further yet, because we also know that if the illumination were known, we could solve for reflectance. This is, really straightforward. If we knew the illumination function, then we could compute the reflectance function as the image we are given divided by the illumination. Since we don't know the illumination, there may be situations where we know it, but since we generally do not know this illumination function, we may try to determine it by means of model fitting. So that is to say, again, we know nothing about what was going on when the image was recorded, but it makes sense for us to assume that the image is in a sense the product of scene illumination and scene reflectance. And it also makes sense for us to assume that compared to the reflectance, the illumination is something that varies slowly, whereas the reflectance may be some really ugly function. All of this makes sense. We still have no idea how the illumination looks like. But if it is a function that varies rather slowly, there are a couple of functions we may assume. Functions that vary slowly are, there are many, but there are sort of fewer functions that vary slowly than functions that vary sort of arbitrarily. As we can, just say, what if the illumination of a scene would vary linearly? This is a slowly varying function. Because we are talking about functions defined over x and y. So what if we could express the illumination, say, as a certain plane? That would be a model we could assume here. Let's say that the illumination function could be expressed as a linear function, which in 2D would correspond to a plane. It was a plane. Can we fit a plane into the image we are given? There are other slowly varying functions, we look at them. But we really don't know if it makes sense to assume that we could express the illumination as a linear function over two variables. But we can just give it a try, see what happens. Okay. So this is what we're going to do. We will today try to fit a plane into the image. Now, the intensity values we are dealing with are numbers between 0 and 255. It is like that if we consider sort of conventional intensity image. And the spatial extension may be large, a couple of thousand pixels times a couple of thousand pixels. And so it appears that what will happen next will have to compute with thousands of values between 0 and 255, and maybe they need to be multiplied and then added together, which is to say the numbers we are dealing with may become very, very large. I'm already, just saying, may become large, and that is, depending on the resolution of the image, if it's a couple of thousand pixels, we may actually run into problems of numerical robustness. If we were to do all of this with pen and paper only, it doesn't matter. But if we try to come up with something that we can do on a digital computer, it is always a good idea to try to avoid over or underflows. Right? You know that. And so I'm just saying we might run in a situation we have to address the problem of overflows here. So this is another thing we just do for the fun of it, for reasons of numerical robustness. We consider the function, and I shall call it L of x and y, and it is called L because it is just the log transform of the image we are given. Now, two things. When I write log, what I really mean is ln, but I don't write it. I don't know why. This is another thing where you have to get used to context. So when I will invert the log transform later on today, and then I will use the exponential function, and then, but this is logarithm with respect to basis 10. No, it's not. Right? So I usually really never write ln, and I don't know, I like to write log. Okay? So this is supposed to be the natural order. Next thing is something you are going to tell me. What will happen if there is a black pixel in this image? A pixel of intensity 0. Yeah, it's undefined. Right. So here is a dirty trick they never tell you about. And because it's such a dirty trick, I will only put it into a window here, and I will not sort of explicitly use it in all of this here. When we do all this on a computer, we somehow read the image f of x, y, somehow it is given, and then we add a 1 to all of it, and that produces a new version of the image. What will now happen if we have a black pixel and compute the log? It's okay. It's okay, right? Because we can compute the log of 1. To our eyes, this is not visible at all. Give it a try. Have an image that consists of only black pixels, visualize it on the screen, and then add a 1 to every pixel. It looks the same. For all intents and purposes, it looks the same. And, they don't tell you about these things, but they all do it. So very likely, if you read something in the literature and you re-implement it, sort of line by line by line by line, and it crashes, because it produces undefined values somewhere, then that tells you that something like that must have happened in the original work, but they consider it so not noteworthy that they don't make it explicit. So I will assume you read an image and you add the 1 to every pixel, because then you can do this then of course sort of the brightest pixel will have a value of 256, but who cares? Mathematics, like this is not nothing, like everything that will happen now is nothing that we actually really want to visualize, not something we just want to compute that we can do. Okay, so this is the dirty trick here for this to work. Dirty trick. Then we can do this. We can compute the log. But this is of course to say, well, if we compute the log of this according to our model, that would mean that this new function L, this log transform image, is basically the log of the reflectance plus the log of the intensity. Right? Because logarithm of product is a sum. And from now on, I will write these two functions. I give them a new name, and this is just because I'm lazy. So this is RL of x and y plus IL of x and y. This is because I'm too lazy to write down log R all the time. And all of this we only do for numerical robustness. Once again, if we would try to tackle what we're going to do next using pen and paper only, we would not need this, but since we want to do this on a digital computer, we have to sort of keep the numbers small, so therefore we do it in log space. Now, but if the intensity is a slowly varying function, well, then the log of the intensity will vary even slower. That is sort of an effect of nature. And now I said, you know, we don't know anything, so let's try something. Let's try something. What we are going to try is fitting a linear model. We really don't know anything. We just, you know, let's make an Ansatz, as it's called, beautiful German word in the English language, Ansatz, which is to express the idea of an informed decision. It's not totally naive, an informed assumption. This is something we call an Ansatz. And we will assume from now on, just because what else can we do, that this function IL of x and y is given as a times x plus b times y plus c. That's what we assume. This is a function over two variables, and it is a plane equation. Right? Because you know, if we assume this to be the x and y direction, then the function IL, depending on how A, B, and C will look like, will be something like this. Some plane somewhere above, or going through the xy. It depends on the parameters. This is what we assume here. But this is therefore to say that we are dealing with the problem of 3D plane fitting. Or also, say estimating a regression plane. And next thing is crucial, therefore I will clean the whiteboard once more. Now that we sort of have realize that the problem we are dealing with is the problem of fitting a regression plane, we can basically say that we can characterize our problem like so. We are given a set of three-dimensional points, xi, yi, and zi, and I ranges from 1 up to some capital N, slightly different than what I said earlier. Another way of saying that is that we are given a set of vectors xi, I ranges from 1 up to capital N, and each of these vectors xi is the three-dimensional vectors xi, yi, zi. Why is that the nature of our problem? It becomes clear if we think about what the zi are, where zi is supposed to be the value of the function I at xi and yi, where we assume once again that this is axi plus b yi plus c. Can you follow me? So basically, you know, we are not really given this function, but we assume that there is something like that there is a function I of xi, yi, which is given by this simple linear expression here in xi and yi. And the value of IL at xi and yi, this is what we call zi. But then we have basically lots of points xi and yi together with their third dimension zi. And depending on the size of the image, you know, we have lots of these points. And I really don't care. I call that the number, you know, it's basically if this is m by n image, then it's the capital M is m by n. You know, depending on the number of pixels, we have very large n's here, but who cares? So this is a very general way of writing down the problem we are dealing with. And given this, we want to achieve the following goal. Our goal is to minimize an objective function. And as always, I will call it E, and it is given as the sum, where I make explicit I ranges from 1 up to n, a times xi plus b times yi plus c minus zi, and it is squared again. We want to minimize all of this with respect to the parameters a, b, and c. Pardon?
Z is given to us.
Yeah. So we assume that z is actually given by the illumination. And we assume that, you know, we don't know the illumination, but basically this is the log of the image, and now this is sort of, we want to fit a plane into the log of the image. All right, so these things are given. Right now, they are definitely not the result of this ansatz here, but we will plug in the values of the log of the intensities of the image. I should probably say that this is sort of the model we have. This is what we want the Z height to be like, but in practice, where do I do this? In practice, that is when we start computing all of this, we have that Zi is, so first of all, Zi definitely depends on xi and yi, and that is L of x. So this is what we will use for our computations. It's a very valid question, and I'm actually really thankful for this question, because to me this is so obvious, but I should probably make this more explicit. Okay, yeah, let's do it. We're almost done. Yeah. Let me erase this and write this differently. So, right now, we have defined this objective function as E being the sum over di, and then A xi plus b yi plus c minus zi squared. If we now introduce, we have already said that we can write the data points we are given as a vector. So xi, yi, zi. This was already there. This is a three-dimensional vector. I can introduce, if we introduce a vector W, let's, just go ahead, A, B, and C. Oh, wait. Okay, I realized that there was a notational mistake on the previous whiteboard. It should not have been a zi, but a 1 here. So please correct that, and what is going to, this is embarrassing, but what is going to happen now is correct. Right? Okay, let me sort of reset this. We introduce vectors xi, let's call them, I don't know, data vectors. Data vector. The first two components are given by xi and yi, so the locations of the pixel. And the third one is given by a 1. Then we can write this here if we also introduce a parameter vector. Parameter vector. We can write this here as, so then A xi plus b yi plus c is in fact the same as the inner product between xi transpose and this parameter vector w. So there was a mistake here. I'll get back to that in a second. Now that is correct. We also introduce this parameter vector here. And we also, if we also introduce a matrix, and on the whiteboard I'm indicating matrices with these two underbars, like so, where the first row contains x1, y1, and 1. The second row contains x2, y2, and 1, all the way up to xn, yn, and 1. Have we seen this before? Yes, we did. Right? We talked about, oh, let's introduce this matrix X, blah, blah. Here it now appears in practice. This is obviously a matrix that has n. This is not natural. Be careful here. Capital N data vectors xi, with this parameter vector w, and with this data matrix x, I can write this error function as the norm of the difference between the vector x times w minus the vector z, and I'll square this, where, and here's the last ingredient, the vector z is given by z1, z2, all the way up to zn. Now, have you ever seen this before? I hope so. If not, I consider this to be, a fact. For those of you where this is not a fact, I would encourage you, I really do, to go to researchgate.net, researchgate.net, search for my name, and for everything I have written in terms of numerical, what is called NumPy SciPy recipes, NumPy SciPy recipes for data science, and that should produce a couple of documents, at least 4 of which deal with least squares optimization. Right? And if you are not familiar with that, then read the first one on ordinary least squares. Ordinary least squares. And maybe you also want to read the second one on nonlinear least squares, because that might come in handy with respect to the exercises. All right, to wrap this all up, because next lecture is about to start. We can write this error like so, and it is another fact of life that the solution of this minimization problem, we have to minimize that with respect to w, is given by w is x transpose times x inverse times x transpose times z. And I said this is a fact of life, and you can actually read the correct reason for why this will be the solution in these lecture notes you'll find on ResearchGate. Here I will just sort of motivate it, but it's not entirely correct, right? It's an intuition. I'll provide you with an intuition. So we are basically dealing with the problem that we want to find w such that matrix x times w gives us z. That could be done if we could invert matrix x, right? We could then basically multiply both sides with the inverse, and we would have the solution. However, this is not a square matrix in general, right? So we can sort of force it to become square by multiplying both sides with x transpose. And that would give us x transpose times x times w is x transpose times z. Now this thing, again, does not necessarily be invertible, but let's assume it was. Then we can multiply both sides with the inverse of that, and then we have w is x transpose times x inverse x transpose z. So there you have it. This is not correct. And even though this is not correct,
it works. and for mathematicians, again, you will have a heart attack right now, so take your heart pills. This is just an intuition why this is the solution here. You can read the perfectly reasonable argument. The result will be the same. But this is invalid. This is not correctly argued here. But if we are given this solution, we now have determined values for these numbers A, B, and C. They are contained in here. They are contained in here. And then we now have a model for the illumination. So then we can compute the reflectance, at least the log reflectance, are at some arbitrary point x and y as L of x and y minus IL of x and y. And IL we cannot compute. We said it's a plane, and we have just determined the parameters of that plane. So we can use it in this equation. We know the minus because of the log, right? But then, this is still all in log space. Let's go for the true reflectance. RL R of x and y is basically the exponential of So what we have done here in a nutshell is, we're given an image, we call it F. We do a dirty trick, add 1 to that, and compute the logarithm, and then we assume that this is basically the same as the sum of some reflectance and some illumination, where we say the illumination is a certain linear function for which we can determine the parameters. Once we have the parameters, we can actually compute the log reflectance. Once we have the log reflectance, we can compute the real reflectance. This is the image we want to get. And this is what I showed you earlier with those cats. All right? That was that in a nutshell. I'll come back to that next time. There are more interesting models we can try here. Are there any questions for today's lecture? Yeah.
Can we call this as a linear regression?
Yes, this is exactly linear regression.
And it quite looks like a maximum likelihood estimation first.
Yes, it is. Very good, yeah. Yeah. So you are familiar with all of this, which is great because you will have a nice time coming up. No, so yes, indeed, this is really a maximum likelihood estimation. Who does see that? Okay, some of you are. This is great. I'm happy about that. For those of you who do not see that, I will not really make this explicit in this course. But in the next semester, when I teach pattern recognition, it will all be about maximum likelihood and how it is related to these squares problems and so on and so forth. But your question was not over yet.
So can you call these W as a vector of Pearl states?
This is a vector, right? I just wrote it down like this because once we have written it like this, the solution here pops out immediately. Where is it? Solution pops out immediately, and please look at the lecture notes as to why that is. And indeed, under the hood, what is going on here is a maximum likelihood computation. But I am not going to talk about this in this course. Any other questions? Great, then we'll see each other again on Thursday, and we'll do the same with a more interesting model. Thank you very much.